Good afternoon. So Zilla Panchayat ವತಿಯಿಂದ ನಡೆಸಲಾಗ್ತಿರುವ CET ಆನ್ಲೈನ್ ಕೋಚಿಂಗ್ ಸೆಷನ್ 6ನೇ ಸೆಷನ್ ಅನ್ಸುತ್ತೆ. ಸೊ ಕೆಮಿಸ್ಟ್ರಿ ಇದು 3ನೇ ಸೆಷನ್ ಕೆಮಿಸ್ಟ್ರಿಗೆ ಸಂಬಂಧಪಟ್ಟಂತೆ. ಸೊ ಅದನ್ನ ಮಾಡಲಿಕ್ಕೆ ಪ್ರೊಫೆಸರ್ ಶ್ರೀಕಾಂತ್ ಸರ್ ಅವರು ಬಂದಿದ್ದಾರೆ. ಅವರಿಗೆ ಸ್ವಾಗತವನ್ನು ಬಯಸ್ತೀನಿ ಕ್ಲಾಸ್ಗೆ.
Good afternoon, dear students. Today we have chemistry class on very first unit, solid state. We have 30 questions. I hope the offline printout copy is with you. So kindly go through the questions one by one. Let us begin with the very first question. The first question is, vacant space in BCC lattice unit cell is about. We have three important types of cubic crystalline systems. They are simple cube, BCC, and FCC. We know the packing efficiency of simple cube is 52.4%. Packing efficiency of BCC is 68%. Packing efficiency of FCC is 74%. What is packing efficiency? It is nothing but total volume occupied by the particles in one unit cell. We have the question vacant space in the BCC lattice unit cell. We know packing efficiency of BCC lattice is 68%. Nothing but in one unit cell, 68% is occupied by the particles. Then vacant space in BCC lattice unit cell is 100 minus 68. It is equal to 32%. So the vacant space in BCC lattice is 32%. Option D. Similarly, vacant space in simple cube is 100 minus 52.4. It is 47.6%. Similarly, vacant space in FCC lattice is 100 minus 74%. It is equal to 26%. Okay. Sometimes students get confused. Whenever they see BCC lattice, immediately they prefer option C, 68%, because packing efficiency of BCC is 68%. But the question is vacant space. So vacant space is 100 minus 68. Therefore, option B, 32%. Next question. How many number of atoms present in a cube-based unit cell having one atom on each corner and two atoms on each body diagonal of the cube? Let us draw one cube. What is given here? One atom on each corner. We know there are 8 corners in a cube. Each corner is occupied by one atom. And we know each corner of a cube is shared by 8 unit cells. Therefore, contribution of each particle per one unit cell is 1 by 8. There are 8 corner particles, each having contribution of 1 by 8. Therefore, total contribution due to all these corner particles is equal to 1. Now, there are 2 atoms on each body diagonal of the cube. How many body diagonals we have? See, body diagonal nothing but line joining the atom present at one face with the particle present in opposite face along the body center. It is one body diagonal. Similarly, we have one more body diagonal from this point to this point. Okay, this is another body diagonal. Likewise, third body diagonal and fourth body diagonal. Totally, we have 4 body diagonals, each having 2 atoms. Therefore, total particles along the body diagonal is equal to 8. See, the particles present in these body diagonal are exactly belonging to this unit cell because they are not shared by any other unit cells. The particles are well inside the cube. Therefore, their contribution is 1 to this unit cell. There are 2 particles on each body diagonal and we have 4 diagonals. So, total number of particles along the body diagonal is equal to 8. So, total number of particles in this unit cell is equal to 8 plus 1 is equal to 9. Therefore, the right option here is option B. Next question. The correct statement regarding the defects in a solid is: Frankel defect is a vacancy defect, Schottky defect is a dislocation defect, trapping of an electron in the lattice leads to the formation of F centers, Schottky defect has no effect on density of solids. Basically, what is a Frankel defect? Frankel defect is nothing but dislocation defect. Let us see, it is solid crystalline systems. The circle represents lattice sites. They are occupied by the particles. Let us assume it is a positively charged particle and a negatively charged particle. They are arranged in alternate positions. What is Frankel defect? It is nothing but shift or dislocation of smaller ion, usually cation, from its lattice site to interstitial site. Because of this shift, density remains the same. Because mass is the same, volume remains the same, density remains the same. Then what is the Schottky defect? Schottky defect nothing but missing of equal number of positively charged ion and negatively charged ion from their lattice site. So, because of missing of these ions from the lattice site, there creates vacancies. Okay, just imagine this positive ion and this negative ion moves away from these lattice sites. This results in creation of vacancy. This is what we call Schottky defect. So, Schottky defect is basically a vacancy defect, whereas a Frankel defect is shift of positively charged cation from its lattice site to interstitial site. Therefore, we call it as dislocation defect. So, Frankel defect should be dislocation, but here it is given that Frankel defect is vacancy defect. It is a wrong option. Schottky defect could be vacancy defect, but here it is given that it is a dislocation defect. Again, a wrong option. Schottky defect has no effect on density. We know Schottky defect nothing but vacancy defect where positive and negative ions from the lattice site. Therefore, mass of the cell decreases, mass of the crystal decreases. When mass decreases, volume must decrease. So, Schottky effect has effect on density of the solid. But here it is given Schottky defect has no effect on density. Again, it is a wrong option. Then what is the correct answer? It is option C. Option C, where trapping of an electron in the lattice leads to the formation of F center. We studied metal excess defect, where negatively charged ion moves from its lattice site to the surface. So the vacant lattice site is occupied by the electron is called F center. Here, trapping of an electron in a vacant lattice site is called F center. That is the right answer. Next question. A metal crystallizes in BCC lattice with edge length of 300 picometer and density 6.15 gram per centimeter cube. The molar mass of metal is, what is given? It is a BCC lattice. BCC lattice means number of particles in one unit cell is 2. Edge length nothing but A, it is given 300 picometer. Nothing but 300 into 10 to the power of minus 10 centimeter or 2 into 10 to the power of minus 8 centimeter. Then density is given, D is equal to 6.15 gram per centimeter cube. We need to calculate molar mass, capital M. We know formula to calculate density of a unit cell is equal to Zm divided by NaAQ. We have to calculate molar mass of the metal. That means we have to calculate M. So M is equal to D NaAQ divided by Z. We know density is equal to 6.15 gram, 6.15. Na is Avogadro number. Avogadro number value is 6.022 into 10 to the power of 23. And A is 2 into 10 to the power of minus 8, 4, 3, divided by Z, number of particles in the 6 into 6 is 36 and we have fraction. Therefore, this product is somewhere 37 and 2 to the power of 3 is 8. Here, 10 to the power of 23 10 to the power of minus 8 cube. It is 10 to the power of minus 24 divided by 2. Divided by 2. Here 2 4 times and 10 to the power of 23 multiplied by 10 to the power of minus 24 is 10 to the power of minus 1. So sorry, edge length is 300. I made a mistake. I wrote it as 200. It is 300. Therefore, it is 3 cube. 3 cube nothing but 27. Sorry, it is 27. Now 37 multiplied by 27 into 10 to the power of 23 and 10 to the power of minus 24. Together it is 10 to the power of minus 1 divided by 2. 37 multiplied by 27 is 1000 into 10 to the power of minus 1 divided by 2. 1000 multiplied by 10 to the power of minus 1 is equal to 100 divided by 2 is equal to 50 gram. So, mass of the metal is 50 gram corresponding to option D. Next question. A metal exists as an oxide with molecular formula M0.96O. Metal M can exist as M plus 2 and M plus 3 in its oxide M0.96O. The percentage of metal M plus 3 in its oxide is. It is a problem based on metal deficiency defect. The formula of the metal oxide is given. It is metal M0.96O1. It is a fraction compared to oxygen. Metal percentage is less than 1. Therefore, it is metal deficiency defect. For my simplicity, let me convert this fraction into whole number. 0.96, let me convert into 96. When it is multiplied by 100, oxygen gets 100. Both sides, I just multiplied by 100. 0.96 converted into 96. 1 is converted into 100. It is just for getting simple answer. You see, if there is a fraction, calculation is bit difficult, so that I am converting into whole number. We know it is a neutral oxide. Metal is positively charged and oxygen is negatively charged. In a neutral oxide, negative charge should be equal to positive charge. Now we have 100 oxygen, each oxygen having oxidation state of -2. So charge on oxygen is -2. Total negative charge in this oxide is equal to -200. To become neutral, metal must have +200 charge. Total charge on metal must be equal to +200. And it is given metal exists in two different oxidation states. One is m plus 2, another one is m plus 3. Let us assume there are x number of m plus 2 ions. Then the number of m plus 3 ion is equal to 96 minus x. Why? Because total number of metal is 96. If x number of m plus 2 ions, remaining ions are in the form of m plus 3. So its number is equal to 96 minus x. The negative charge, total negative charge in the oxide is minus 200. So we must have plus 200 charge due to all these metals. Okay. Now x number of m plus 2 ions, x number of m plus 2 ions having charge plus 2 and 96 minus x number of m plus 3 ion whose charge is plus 3. The total charge should be equal to plus 200 in order to become electrically neutral. So it is 2s plus 96 into 3. It is 6 into 3, 18. 9 into 3, 27 plus 1, 288 minus 3x is equal to 200. Or minus x plus 288 is equal to 200. Or x is equal to 88. X is equal to 88. X nothing but number of m plus 2 ion is 88. Then the number of m plus 3 ion is 96 minus x, nothing but 88. It is equal to 8. Number of m plus 3 ion is equal to 8. The question is percentage of m plus 3 ion in its oxide. How to calculate percentage? It is number of m plus 3 ion divided by total number of metal ions. How many number of metal ions we have? Total number of metal ion is equal to 96 multiplied by 100. After calculation, we get 8.3 percentage. 8.3 percentage. So the percentage of m plus 3 ion in its oxide is 8.3 percentage, nothing but option A. Next question. A metal crystallizes in FCC structure with the metallic radius root 2a. The volume of the unit cell in the meter cube is. Sorry. The volume of the unit cell in the meter cube is. What is given? Crystallizes in the FCC structure with the metallic radius. Radius nothing but r. R is equal to root 2 angstrom. Nothing but root 2 into 10 to the power of minus 10 meter. We have to calculate volume of the unit cell. What is the formula to calculate volume? Volume of unit cell is represented by A cube. A is edge length of the unit cell. So to calculate volume, we must know the value of A, edge length of the unit cell. How to calculate A? We know R and the system is FCC. There are three systems: simple cube, BCC and FCC. They are the three important cubic crystalline systems. In simple cube, relationship between A and R is A is equal to 2R. In BCC, A is equal to 4R by root 3, and in FCC, A is equal to 2 root 2R. These are the relationship between edge length of the unit cell and radius of the particle. The system here is FCC, therefore required relationship is A is equal to 2 root 2R. R is given, A is equal to 2 into root 2, R is root 2 angstrom, nothing but root 2 into 10 to the power of minus 10. Root 2 is 2 multiplied by 10 to the power of minus 10. 2 into 2 is 4 into 10 to the power of minus 10 meter. It is just edge length. We have to calculate what? We have to calculate volume of unit cell A cube. Therefore, A cube is 4 into 10 to the power of minus 10 whole cube. 4 cube is nothing but 64. 10 to the power of minus 10 cube is 10 to the power of minus 30. Now let us see where this option is present. 64 into 10 to the power of minus 30. We can see option D where it is given that 6.4 into 10 to the power of minus 29, right? 64 into 10 to the power of minus 30 is one and the same as 6.4 into 10 to the power of minus 29. Both are same. Therefore, the right answer here is option D, 6.4 into 10 to the power of minus 29. That is the volume of the unit cell. Next question. Silicon doped with intrinsic semiconductor, both N and P type semiconductor. We know silicon and germanium are intrinsic semiconductors. They are the members of group 14 elements. Group 14 elements are carbon, silicon, germanium, tin, and lead. What is the common oxidation state of group 14 elements? It is +4. Means they are tetravalent, having 4 valence electrons and forming 4 covalent bonds. Let us write silicon. It is a tetravalent having 4 electrons. It forms 4 covalent bonds with the neighboring silicon atoms in its solid crystalline lattice. So it forms covalent bond with the neighboring silicon atom. It goes like this in a 3-dimensional structure. Okay. Now let us imagine previous group 13, and next group 15. Group 14 elements are tetravalent. Group 15 elements are pentavalent. Pentavalent nothing but they have 5 valence electrons. Similarly, group 13 elements are trivalent. Nothing but they have 3 valence electrons. Now, the group 15 members are nitrogen, phosphorus, arsenic, antimony, bismuth. And group 13, boron, aluminium, gallium, indium, and thallium. When group 14 element, silicon and germanium, is doped by group 15 element, we get 1 electron more compared to that of silicon. Let us assume silicon is replaced by one of the group 15 element like phosphorus. We know phosphorus is a pentavalent having 5 valence electrons. Silicon is having 4 electrons. Phosphorus is having 5 electrons. When 4 tetravalent silicon is replaced by pentavalent phosphorus, we get 1 electron more compared to original silicon. Because of the presence of more electron, we call it is N-type semiconductor. N-type semiconductor. At the same time, when a trivalent atom like boron, aluminium, gallium, indium, thallium is added into intrinsic semiconductor, the tetravalent silicon is replaced by one of the trivalent atom, for example, gallium. When the gallium is added, we know it is a trivalent having only 3 valence electrons. There is a shortage of 1 electron. Silicon is having 4 electrons, gallium having only 3 electrons. Therefore, there is a shortage of 1 electron. Deficiency of 1 electron is termed as a positive charge. Therefore, they are called as P-type semiconductors. Okay. Here, silicon is doped with gallium. Gallium is group 13 element. Therefore, it forms P-type semiconductor. That is option B. If the question is silicon doped with nitrogen, phosphorus, arsenic, or any other group 15 element, then the answer will be N-type semiconductor. Okay. Next question. An element has BCC structure with the cell edge of 288 picometer. The atomic radius is, the system is BCC. BCC. So cell edge nothing but A, given 288 picometer. We have to calculate R, what is the atomic radius. About 2-3 minutes back, I told there is a relationship between A and R in simple cube, BCC and FCC. The system here is BCC. In BCC, A is equal to 4R by root 3. 4R by root 3. A is given, it is 288 picometer. It is equal to 4 by root 3 into R. We have to calculate radius. Therefore, radius is equal to 288 into root 3 goes to left hand side into root 3 divided by 4. Divided by 4. So this option is 4 in root 3 into 288. Root 3 into 288 picometer divided by 4. So the right answer is B. Next question. Which of the following is a network crystalline solid? See, solids are of 4 types. One is ionic solid. Second one, covalent solid. It is also called network solid. Third one, molecular solid. Molecular solid. Fourth one, metallic solid. Metallic solid. Ionic solid is made by ionic compounds. So one example for ionic compound is NaCl. It is ionic molecule, plus charge on sodium, minus charge on chloride ion. So these two are ions bound by ionic bond. Such solids form ionic solids. Let me go for third one, molecular solid. It is made by molecules, say oxygen molecule, hydrogen molecule, nitrogen molecule, chlorine molecule, iodine molecules. These molecules, when solidify, form molecular solids. Metals form metallic solids. Then what about the covalent solid or network solid? It is mainly made by non-metals, which having extensive cross-linking through covalent bond to form a giant molecule, macromolecule. One example is diamond, where we have large number of carbon atoms tetrahedrally linked with each other through covalent bond, forming a network crystal. In the same way, we have several examples for network crystals. They are graphite, aluminum nitride, silicon carbide, etc. Okay. Here, there are 4 options. Iodine is a molecule. Therefore, it is an example for molecular solid. Sodium chloride is an ionic crystal. Therefore, forming ionic solid. I is basically a water molecule. I is nothing but solid water. Solid water. H2O is a molecule, therefore it is forming molecular solid, and it can involve in intermolecular hydrogen bonding with another water molecule. Therefore, we call hydrogen bonded molecular solid. Aluminium nitride form a macromolecule due to extensive cross-linking by covalent bond. Therefore, aluminium nitride is an example for covalent or network solid. Okay. Among the 4 options, the right answer is B, aluminium nitride. Next question. The number of atoms in a 2.4 gram of BCC crystal with edge length 200 picometer each. Let us see what are the data given. The mass of the crystal atom is 2.4 gram. It is BCC crystal, so number of particle in 1 unit cell is 2. Edge length is given. A, it is equal to 200 picometer. Density is given. It is 10 gram per centimeter cube. We have to calculate number of atoms present in 2.4 gram. Number of atoms present in 2.4 gram. To calculate number of atoms in 2.4 gram, we must know one standard. What is the standard here? We know 1 mole of any substance consisting of Avogadro number of particles. 1 mole of any substance consisting of Avogadro number of particles. We represent Avogadro number here as Na. So let us calculate molar mass of the substance. Molar mass. Just imagine molar mass is x gram. Then x gram of that crystal will have Avogadro number of particles. Once we know molar mass, we can easily calculate 2.4 gram consisting of dash number of atoms. Okay. Then how to calculate molar mass? We know formula B is equal to Zm divided by Na AQ. We have to calculate molar mass M. Therefore, M is equal to D Na AQ divided by Z. Density is given. It is 10. Avogadro number is 6.022 into 10 to the power of 23. And edge length A is 200 picometer. Let me write it as 2 into 10 to the power of minus 8 centimeter. 200 picometer, nothing but 2 into 10 to the power of minus 8 centimeter. And it is a whole cube divided by Z value is 2. 10 into 6.022 and into 10 to the power of 23. It is 6.022 into 10 to the power of 24. 10 is multiplied by 10 to the power of 23. It is 10 to the power of 24. 2 cube is 8 multiplied by 10 to the power of minus 8 cube is 10 to the power of minus 24 divided by 2. 10 to the power of plus 24 minus 24 get cancelled with each other. 2, 4 times 8. Now 6 and 4. When you multiply these values, we get nearly 24 gram. 24 gram. It is molar mass of this substance. Now 24 gram is molar mass. Therefore, 24 gram has Avogadro number of particles, Avogadro number of atoms or particles. What is given here? We have taken just 2.4 gram of the substance. 24 gram has Avogadro number, then the 2.4 gram has dash number of particles. What we do? We just cross multiply. 6.022 into 10 to the power of 23 into 2.4 divided by 24. It is equal to 6.022 into 10 to the power of 22. 10 to the power of 22. Where this option we can see, it is option way A, 6 into 10 to the power of 22. So the number of atoms in the 2.4 gram of this crystal is 6.6 into 10 to the power of 22. Next question. 1 mole of NaCl is doped with 10 to the power of minus 5 moles of strontium chloride. The number of cationic vacancies in the crystal lattice will be. Let us draw a solid crystal. Assume it is NaCl. NaCl has Na plus and Cl minus ions. Let us assume it is Na plus Cl minus, Na plus Cl minus. Here Cl minus, Na plus, Cl minus, Na plus, Cl minus.
ಸರಿ ಸರಿ
What is given? 1 of NaCl minus 5 moles of strontium chloride. We know charge on one sodium ion is 1, positive 1. Charge on one strontium ion is plus 2. In order to become electrically neutral, one strontium ion must replace 2 sodium ions. The reason is sodium having just plus 1 charge, but strontium having plus 2 charge. When one strontium comes into the crystal, 2 sodium ions must be kicked out. Okay. 2 vacancies are created when 2 sodium ions are removed from the crystal. Remember, when 2 sodium ions are removed, one of the lattice site is occupied by strontium. It came into the vacant site of this crystal. So out of the two, one of the vacant site is occupied by strontium ion, another lattice site is remain vacant. What I mean to say, when one strontium ion enters into the crystal, one vacant lattice site is produced. One vacant lattice site is produced. Now, how many strontium ions are coming? There are 10 to the power of minus 5 moles of strontium chloride. Each strontium chloride having 1 strontium ion, 10 to the power of minus 5 moles having 10 to the power of minus 5 strontium ions. Remember, 1 strontium ion can create 1 vacancy. So 10 to the power of minus 5 moles of strontium ion can create 10 to the power of minus 5 moles of vacancy. Moles of vacancy. 10 to the power of minus 5 moles, nothing but 10 to the power of minus 5 mole, nothing but Avogadro number 6.022 into 10 to the power of 23. When you multiply Avogadro number with 10 to the power of minus 5, answer is 6.022 into 10 to the power of 18. So number of vacancies in the crystal lattice will be 6.022 into 10 to the power of 18, corresponding to option A. Next question. In FCC, the unit cell is shared equally by how many unit cells? You know, a cube having 6 faces. Cube having 6 faces, each face having 1 face-centered particle. Face-centered particle. In the solid, each face is shared by another cube. Each face is shared by another cube. We know there are 6 faces. Each face is shared by another cube. Therefore, number of faces shared equally by another unit cell is equal to 6. Very simple question. Total number of unit cells shared equally by one unit cell. Next question. In a FCC cell, A atoms are at the corners and B atoms are at the face centers. If one of the A atoms is missing from one corner, then the simplest formula of the compound is a cube. It is a cube having 8 corners and 6 faces. There are 6 faces. What is given? All the corners are occupied by A atoms. These are the corners occupied by A atoms, and face centers are occupied by B atoms. B atoms. If one of the A atom is missing from one corner, before going into this point, let us finish the first sentence. There are A particles at each corner. We know there are 8 corners in a cube. Each corner is shared by how many unit cells? Each corner of a cube is shared by 8 more unit cells. Therefore, contribution of one unit cell is 1 by 8. 1 by 8. Right? So, number of A particle in this unit cell is equal to 8 into 1 by 8. At the same time, there are 6 face-centered particles occupied by B. There are 6 face centers. Each face of a cube is shared by one more neighboring cube. Therefore, contribution of this face-centered particle per one unit cell is half. Okay, it is the data given in first sentence. Now, in the second sentence, one of the A atom is missing from one corner. We have 8 corner particles. Out of 8, one of the particle is missing. Then total number of corner particle is just 7, not 8. So number of A particle will be 7 into 1 by 8, whereas number of B particle will be 6 into half. Nothing but, let us write the ratio. A is to B is equal to, A contribution is 7 into 1 by 8 and B contribution 6 into half. So it is not working, sorry. 6 into half. 6 into half. Nothing but 7 by 8 is to, it is 3. Or 7 is to 8 is taken to that side, it is 24. What is the ratio? A corresponding to 7, A corresponding to 7, B corresponding to 24. B corresponding to 24. Therefore, the molecular formula of this crystal, when one of the corner particle is missing from its lattice site, is A7, B24, corresponding to option A. Next question. If same type of atoms are packed in HCP and CCP separately, then density of HCP is greater than that of CCP. Density of CCP is greater than that of HCP. Density of both HCP and CCP are same. None of these. We know packing efficiency of HCP is equal to CCP is equal to FCC, that is equal to 74%. Packing efficiency of HCP and CCP both are equal to 74%. 74%. They are occupying equal space in the unit cell. Means their volume is same and same type of atoms are packed. Nothing but their mass is same. When the mass is same, volume is same, density should be same. Okay. Therefore, the right option here is density of both HCP and CCP are same. Next one, a crystalline solid XY3 has CCP arrangement for its element Y. Then X occupies 33% of tetrahedral whites, 50% of tetrahedral whites, 66% of octahedral whites, 33% of octahedral whites. The formula given here is XY3, or you can write it as X 1 by 3 Y1, or X 0.33 Y1. Nothing but when number of Y particle is 100, number of X particle should be equal to 33. X 33 Y 100. When number of Y particle is 100, X should be equal to 33. or when it is 100%, y is 100%, x should be 33%. Now let us assume there are n number of y particles. N number of y particles. Here it is given that CCP crystal made by element y. The whole crystal is made by element y. Let us assume there are n number of lattice sites in the crystals occupied by y. We know when there are n number of lattice sites, there will be n number of octahedral whites and 2n number of tetrahedral whites. 2n number of tetrahedral whites. So there are n number of y particle. According to this stoichiometry, when there are n number of y particle, x should be equal to 0.33 times m. 0.33 times m or 33% of m. 33% of m. Nothing but if there are n number of octahedral whites, only 33% of octahedral whites should be occupied by x. Then only this stoichiometry is formed. Or there are how many tetrahedral whites? 2n number of tetrahedral whites. 2n number nothing but 100%. We must have only 33% occupancy. It is nothing but 33 into 2n divided by 100 equal to 16.5%. What I mean to say, either x particle must occupy 33% of octahedral white or 16.5% of tetrahedral whites available in the crystal. So the right option among the four is x can occupy 33% of octahedral whites. Tetrahedral white means it must occupy 16.5, but we cannot find that option. 16.5% of tetrahedral white is not given. Therefore, the only right answer is D, 33% of octahedral whites. Next question. In a face-centered cubic lattice, atom A occupies the corner and atom B occupies the face center positions. If one atom of B is missing from its position, the formula of the compound is. It is a face-centered lattice. Basically, a cubic crystal where particles present at the corner as well as the face center. A occupies corner positions. So these positions are occupied by A and face centers are occupied by B. How many A particle? We know there are 8 corners in a cube and each corner having a contribution of just 1 by 8 per 1 unit cell. So total number of A particle is equal to total number of A particle is 8 into 1 by 8. 8 into 1 by 8. Whereas number of B particle is equal to 6 face centers, each having contribution of half. So total number of B particle is equal to 6 into half. It is A, it is B. Let us write the ratio. A is to B is equal to 8 into 1 by 8, 6 into half. Now it is given that one atom of B is missing from its position. Out of 6 B particles, one of the particle is missing from its position. Therefore, only 5 particles available at the face centers. So the simple ratio is 8 into 1 by 8 is to 5 into half. After simplification, it is 1 is to 5 by 2. Or 2 is taken to this side, it is 2 is to 5. So A is to B is equal to 2 is to 5, nothing but A contribution is 2, B contribution is 5. The formula will be A to B5, nothing but option A. Next one, lithium forms body-centered cubic crystal. The length of the side of the unit cell is 351 picometer. Atomic radius of the lithium will be. We have solved a similar kind of a problem, but there we calculated edge length. Here we have to calculate radius of the particle. Okay, the system here is body centered cubic crystal BCC. Therefore, relationship between A and R is A is equal to 4R by root 3. What is given? Length of the side of the unit cell, edge length is given. It is equal to 351 picometer, equal to 4 by root 3 into R. We have to calculate radius of lithium. R is equal to 351 into root 3 divided by 4. Nothing but 351 into root 3 value is 1.73 divided by 4. If you simplify, we get 152 picometers. 152 picometer. Therefore, right answer is C. Next one. The coordination number of a cation occupying a tetrahedral void in a crystal is. We know there are two types of voids. One is octahedral void, second one is tetrahedral void. What is octahedral? Any vacant site, interstitial site surrounded by 6 number of particles, then it is called octahedral void. Any void or interstitial site surrounded by only 4 particles, then we call it as tetrahedral void. Okay, here the question is tetrahedral void, coordination number of tetrahedral void, nothing but a void covered by 4 particles or connected to 4 particles. What is coordination number? It is the number of particles which are in direct contact with one particle. Here our focus is on tetrahedral void, which is directly in contact with the 4 neighboring particles. Therefore, coordination number of tetrahedral void is 4. If the question is coordination number of octahedral void, then the answer will be 6. Okay. Next question. The flame colors of metal ions are due to. It is maybe due to metal excess defect, metal deficiency defect, Schottky defect, and Frankel defect. Now, flame color of metal ions are due to. We studied in our theory class that NaCl crystal shows metal excess defect. Metal excess defect. Just imagine it is NaCl crystal where Na plus ion is attached to Cl minus ion and vice versa. Positive is Na plus, negative is Cl minus. Just imagine this sodium chloride is heated in atmosphere of sodium vapors. There will be certain number of sodium atoms on the surface of a sodium chloride crystal. When there is free sodium atom on the surface of a sodium chloride crystal, the chloride ion shifts from its lattice side to the surface in order to interact with this free sodium atom. When this chloride ion shifts from the lattice side to the surface, this lattice site become vacant. Okay, here we have sodium atom on the surface. Chloride ion shifts into surface. Remember, chloride ion needs only sodium ion to interact because these two oppositely charged ions forming a molecule of NaCl. So sodium loses its one of the electron, undergoes ionization to Na plus. After converting into Na plus, it interacts with the chloride ion coming from its lattice site. Means one electron is ejected from sodium atom. That free electron comes back to this vacant site, which is already created due to the shift of chloride ion from this lattice site to the surface. Now, this vacant site occupying electron is called F center. So we have a free electron in this solid crystal. When heat energy is given to this crystal, the free electron undergoes excitation and undergoes vibrational motion. Because of that, some amount of energy is emitted, having wavelength corresponding to visible region that gives a characteristic color. So here, color of NaCl is due to the presence of free electron in vacant site. Now you can see in our earlier case, original crystal, where we can see 3 positive ions in the first layer and 2 negative ions. Second layer, 3 negative ions, 2 positive ions. Nothing but 5 sodium ions and 5 chloride ions. Equal number of sodium ions, equal number of chloride ions. When chloride ion shifts from its lattice site to the surface, one of the chloride moves from its lattice site. Number of chloride ion in the crystal becomes 4. Now there are 5 sodium ions, only 4 chloride ions. There is one extra sodium metal ion, therefore we call it as metal excess defect. Metal excess defect. The free electron is responsible and this free electron is produced due to the metal excess defect. Next question. Tungsten crystallizes in a cubic lattice structure and its density is 19.25 gram per centimeter cube. If the edge length of the unit cell is 3.165 angstrom, the type of the unit cell is. The options are simple cube, BCC, FCC, edge-centered cubic lattice. We know simple cube has only one particle per unit cell. BCC has 2 particles per unit cell. FCC has 4 particles per unit cell. What do you mean by edge-centered cubic lattice? We have a cube. Of course, there will be particles at the corners, 8 corners, each having 1 particle. And how many edges in this cube? You see, in the upper face, where you can find 4 edges. In the bottom face also, we have 4 edges. 4 plus 4, 8. Left side face, 2 edges, 10. Right side, 2 edges, plus 2, 12. So total number of edges is equal to 2. Each edge will have a particle, then it is called edge-centered cubic lattice. Remember, each edge of unit cell is shared by 4 unit cells. Just imagine it is a cube. It is connected to one more cube on the right hand side. Above these 2 cubes, we can have 2 more cubes. Totally, this edge can share its edge with 4 unit cells. Means its contribution is just 1/4 per 1 unit cell. Now 12 into 1/4 is equal to 3, and there are 8 corner particles whose contribution is 1. Total number of particles in edge-centered cubic lattice is 4. Okay. Now, if we could able to calculate number of particles present in 1 unit cell, we can identify the type of crystal. So let us calculate number of particles present in one unit cell. How to calculate? We have the formula D is equal to Zm divided by Na AQ. We need to calculate Z. Therefore, Z is equal to dNA AQ divided by M. Density is given. It is 19.25. Na is Avogadro number 6.022 into 10 to the power of 23. A is edge length. Edge length is 3.165 Armstrong, 10 to the power of minus 10. When it is converted to centimeter, it is 10 to the power of minus 8 cube divided by molar mass of tungsten is given. It is 184. After simplification, we get answer 2. Number of particle is equal to 2. 2 nothing but it is body centered cubic crystal BCC. Therefore, right answer is B, option B. Next question. A metal oxide crystallizes in a HCP array of oxide ions with every 2 out of 3 octahedral voids occupied by metal ions. The formula of the oxide is metal oxide crystallizes in a HCP array of oxide ions with every 2 out of 3 octahedral voids occupied by metal. What it is? HCP crystal is formed by which ion? It is formed by oxide ions. All these lattice sites occupied by oxide ions. Then where is metal? Metal present in 2 out of 3 octahedral voids. Between the lattice sites, we have 2 types of voids. We call it as either octahedral void or tetrahedral void, depending on the number of particles surrounding this void. We know if there are n number of lattice sites, there will be n number of octahedral void and 2n number of tetrahedral void. Just imagine there are n number of lattice sites occupied by oxides. So number of oxide is n. Then number of metal. It is given that 2 out of 3 octahedral voids are occupied by metals. How many octahedral voids we have? We have n number of octahedral voids. Only 2 out of 3, nothing but 2 by 3 number of octahedral voids are occupied by metals. Therefore, the ratio is metal is 2 by 3 times number of lattice sites and number of oxide ion is n. N get cancelled. It is 2 by 3 is to 1 or 2 is to 3. Means metal corresponding to 2, M2, oxygen or oxide corresponding to 3, O3. Molecular formula will be M2O3. Right answer is option D. Next one. The unit cell with the crystallographic dimensions but it is not equal to beta is. Options are monoclinic, tetragonal, triclinic, and orthorhombic. Let me first clarify. The answer is monoclinic. This crystallographic dimension is corresponding to monoclinic. Then what is crystallographic dimension for tetragonal? For tetragonal, A is equal to B, but it is not equal to C. Alpha is equal to beta is equal to gamma is equal to 90 degree. For triclinic, A is not equal to B, not equal to C, alpha not equal to beta, which is not equal to gamma. Most disaster is with triclinic. Sorry, disorder is with the triclinic. Then third one, sorry, in among the options, fourth one, orthorhombic. Orthorhombic is A not equal to B not equal to C, alpha is equal to beta which is equal to gamma. These are the different crystallographic dimensions. The given dimension matches with only monoclinic, therefore right answer is A. Next one, in a cubic closed packed structure of metal oxides, the lattice is made up of oxide ions. 20% of tetrahedral whites are occupied by divalent X plus 2 ions. 50% of octahedral whites are occupied by trivalent Y plus 3 ions. Then the formula of oxide is, we have three types of ions. One is oxide ion, another one is divalent X plus 2 ion, third one is trivalent Y plus 3 ions. Oxide forms cubic closed packed structure, means all the lattice sites are occupied by oxide ions. These lattice sites are occupied by oxide ions. Let us assume there are n number of lattice sites, they are occupied by oxide ions. Now, X plus 2 ion occupies 20% of tetrahedral whites. We know there are 2n number of tetrahedral whites for n number of lattice sites. 2n number of tetrahedral whites, only 20% is occupied, nothing but 20 divided by 100. Percentage means 20 divided by 100. These many number of tetrahedral whites are occupied by X. Then Y, it occupies 50% of octahedral whites. We know there are n number of octahedral whites, only 50% is occupied. Nothing but 50 by 100 now times n is occupied by trivalent Y plus 3 ions. Just to simplify it, it is 1, then 20 into 2 is 40 divided by 100, then 50 by 100. Let me multiply these three values by 100 so that it is 100 is to 40 is to 50. Or if you further simplify, it is 10 is to 4 is to 5. Nothing but oxide is 10, X plus 2 is 4, Y plus 3 is 5. Let me write X having contribution 4, Y 5, oxygen 10. Molecular formula is X4 Y10, sorry, Y5 O10. X4 Y5 O10. Right answer is B. Next question. What type of defect is indicated in the diagram given below? Options are Frankel defect, Schottky defect, interstitial defect, and non-stoichiometric defect. What is the Frankel defect? Frankel defect is nothing but it is dislocation of cation from its lattice site to the interstitial site. Just imagine here there is a cation, sodium ion. If it may shift from its lattice site to somewhere here, interstitial site, then we call it as Frankel defect. What is a Schottky defect? Missing of equal number of cation as well as anion, so that stoichiometry is retained. Stoichiometry should be retained. Then it is called Schottky defect. Interstitial defect is nothing but a Frankel defect itself, where one ion its regular lattice site to interstitial site. Another name for Frankel defect. Non-stoichiometric defect nothing but the defect leads to loss of stoichiometry. Unequal number of missing of ions leads to non-stoichiometric defect. Let us see how many number of ions are missing here. Here, one chloride ion is missing, one sodium ion is missing, one chloride ion is missing, one sodium ion is missing. Total, there are two sodium ions are missing and two chloride ions are missing. We know molecular formula of sodium chloride is NaCl, Na having positive charge, Cl having negative charge. If two sodium ions, two chloride ions are missing from the lattice side, we get back the same molecular formula. There is no harm to the molecular formula, means stoichiometry is retained. So loss of ions leading to having same stoichiometry called as a Schottky defect. Loss of positive and negative ions such that stoichiometry is retained, it is called Schottky defect. Therefore, among the four options, the structure corresponding to Schottky defect, option B. Next one, total number of voids in 0.5 mole of a compound forming HCP structure are. We know in any crystal, just imagine there are n number of lattice sites, then there will be n number of octahedral voids and 2n number of tetrahedral voids. So total number of voids will be 3n. 3n. Okay. Now what is given? We have 0.5 mole of a compound. For n number of particles, we have 3n number of voids. Then for 0.5 mole of a compound, we must have 3 times of 0.5 mole of voids. 3 times 0.5 mole of voids. It is nothing but 3 into 0.5 mole, nothing but Avogadro number 6.022 into 10 to the power of 23. 3 into 0.5 is 1.5 multiplied by Avogadro number. 6.022 multiplied by 1.5 is 9.033 into 10 to the power of 23. These many number of voids present in 0.5 mole of the compound. So 9.033 into 10 to the power of 23, nothing but right answer is D, option D. Next one, the number of unit cells in 4 gram of a compound having molecular mass of 40 gram, which crystallizes in BCC pattern is. The crystal system is BCC, molar mass capital M is 40 gram. We have taken 4 gram of compound. The question is, how many number of unit cells present in 4 gram? How to calculate? We have standard 1 mole, nothing but molar mass 40 gram, 1 mole of any substance consisting of Avogadro number of particles 6.022 into 10 to the power of 23 particles. Generally, we represent Avogadro number as Na. 40 gram has these many particles. We have how many grams? Just 4 grams. 4 grams. Then it has how many particles? What we do? We just cross multiply 4 into Avogadro number divided by 40. It is equal to 0.1 into Avogadro number. These many particles present in 4 gram. But the question is, how many number of unit cells present? We have these many particles. Question is, how many number of unit cells present? Remember, it is a BCC crystal. BCC unit cell has two particles. One unit cell has two particles. Or if you rearrange, two particles forming one unit cell, right? Two particles together forming one BCC unit cell. We have how many particles? 0.1 into Na, Avogadro number. These many particles we have, they together form how many unit cells? Again, we need to cross multiply. It is 0.1 into Avogadro number divided by 2. 0.1 into Avogadro number divided by 2. It is nothing but right option C, 0.1 Na divided by 2. These many number of BCC unit cells are formed by 0.1 into Avogadro number of particle, nothing but 6.022 into 10 to the power of 22 particles. Okay, next question. A mineral of titanium is found to contain calcium atoms at the corners, oxygen atoms at the face centers, and titanium at the center of the cube. Oxidation number of titanium in the mineral is, we have a cube. Here, calcium atom are at the corners. Corners are occupied by calcium atoms. Of course, ions. Oxygen atoms are at the face centers. These face centers are occupied by oxygen. And body center, center of the cube, nothing but body center, which is occupied by titanium. Titanium. We have to find out oxidation state or oxidation number of titanium. Let us write the molecular formula first. We have 8 corners. Each corner is occupied by calcium. So number of calcium is, there are 8 corners, each having contribution of 1 by 8 per unit cell. So total number of calcium atoms per unit cell is 1. What about oxygen? Oxygen present at the face center. How many face centers we have? We have 6 face centers, each having contribution of half. Each face is shared by one more unit cell. Therefore, contribution of this particle per one unit cell is half. So, total number of oxygen is equal to 3. How many titanium atoms? Only one titanium is present because it is present at the body center. One cube can have only one center and it is not shared by any more unit cells. So its contribution per one unit cell is 1. Nothing but formula is calcium 1, oxygen 3, titanium 1. What is the oxidation state of calcium? It is +2. Oxidation state of oxygen -2. Oxidation state of titanium, we have to calculate, that is unknown. Let us take it as X. Remember, it is a neutral molecule, so that sum of oxidation state should be equal to 0. Okay, now we have one calcium whose oxidation state is +2 and 3 oxygen having oxidation state of -2 and one titanium whose oxidation state is X. Sum of these oxidation state should be equal to 0 as the molecule is neutral. So it is 2 minus into plus minus 6 plus X is equal to 0, or X is equal to 2 minus 6 is -4. It goes to right hand side and converted into +4. Nothing but oxidation state of titanium is +4. Right answer is option D. Next one, substance which is weakly repelled by the magnetic field is. Options: oxygen, nitrogen, chromium dioxide, and magnetite, Fe3O4. We know there are three important types of magnetic substances. They are diamagnetic, paramagnetic, and ferromagnetic substances. Of course, there are two more called ferrimagnetic and antiferromagnetic substances. What are diamagnetic substances? They are the substances which are repelled, weakly repelled by external magnetic field, called as a diamagnetic substance. Paramagnetic substances are those attracted by external magnetic field. Ferromagnetic substances are those which are strongly attracted by the external magnetic field. Now, oxygen is what kind of magnetic substance? We know oxygen having one oxygen atom having atomic number 8 electrons. One oxygen molecule, we have two oxygen atoms. Together, it is having 16 electrons. If you write electronic configuration of oxygen molecule, its electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p x2, pi 2p y2, pi 2p z2, pi star 2p y1, pi star 2p z1. Nothing but we have two unpaired electrons. When there are unpaired electrons, they itself act as a magnet. In the presence of external magnetic field, these unpaired electrons are attracted towards external magnetic field. Therefore, oxygen acts as a paramagnetic substance. Whereas nitrogen, total number of electron in nitrogen molecule is 14, means 2 electron less compared to oxygen. We have to remove outermost 2 electrons, then we get electronic configuration of nitrogen. It is up to pi 2pz2. Means all these molecular orbitals having paired electrons, only paired electrons. The paired electrons have magnetic moment in opposite direction. So net magnetic field created by paired electron is 0. Therefore, it acts as diamagnetic substance. We know diamagnetic substances are weakly repelled by external magnetic field. Weakly repelled by external magnetic field. Therefore, the right answer is option B, nitrogen, which is repelled by external magnetic field, whereas oxygen is a paramagnetic, attracted by external magnetic field. Chromium dioxide is a ferromagnetic, means it is strongly attracted by external magnetic field, and magnetite, Fe3O4, act as ferrimagnetic substance, a kind of ferromagnetic substance but having weak magnetic moment. Therefore, it is called as ferrimagnetic substance. So only nitrogen is a diamagnetic, therefore it is repelled by external magnetic field. 29th question. Which of the following condition favors the existence of a substance in the solid state? We have three important types of crystalline systems, matter, physical state of matter. They are solid, liquid, and gas. Solid, liquid, and gas. What is the main difference? In case of solids, particles are in contact with each other. In case of liquid, particles are little away from each other. In case of gases, there is maximum disorder. Particles are very far away from each other. Now, at high temperature, which physical state is favored? We know when temperature is increased, kinetic energy of the particle increases, mobility increases, that leads to gaseous state. Whereas low temperature leads to decrease in kinetic energy, particles start to aggregate together so that it leads to formation of solid state. Therefore, which of the following condition favors the existence of a substance in the solid state means low temperature favors the existence of solid state. If you go to option C, high thermal energy, it is just similar to high temperature. When energy is provided, kinetic mobility of the molecule increases, that leads to conversion of a solid into liquid and then into gas. Therefore, it cannot leads to the existence of the substance in a solid state. And the fourth option, weak cohesive forces. Weak cohesive force, nothing but weak dispersion force. We know solids can be possible only if there is a strong attractive force between the particles. Weak cohesive force leads to gaseous state. So out of the four options, only option B, low temperature, favors the presence of substance in the solid state. Last question, which of the following exhibits both Frankel and Schottky defect? We know Frankel defect is nothing but dislocation of particle from its lattice site to interstitial site. It is formed when there is a large difference in size of cation and anion. Most probably, it is shown by silver salts like AgCl, AgBr, AgI, and even in zinc sulfide, where there is a large difference between size of cation and size of anion. In such case, we observe Frankel defect. Whereas Schottky defect is the one where missing of both cation and anion occurs from their lattice site. It is possible when there is a similarity in size between cation and anion. It is shown by alkali metal salts like NaCl, KCl, rubidium chloride, cesium chloride, and so on. Alkali metal salts show Schottky defect because of the similarity in size of cation and anion. Means zinc sulfide shows Frankel defect, cesium chloride shows Schottky defect, sodium chloride shows Schottky defect. Schottky defect is one special molecule which shows both Frankel defect as well as Schottky defect. Both Frankel and Schottky defect is shown by AgBr. Therefore, among the following, the one exhibiting both Frankel and Schottky defect is AgBr. These two molecules show only Schottky defect. Zinc sulfide shows only Frankel defect. Okay. It is the last question, 30th question. With this, let us wind up today's class. Thank you for your time.
It's 4:29 p.m. It's 4:29 p.m.